Hello, everyone. Thank you for coming. Here's another knowledge share. This one is on an introduction to PyTest, and it's a fairly simple level. It's aimed at QA folk who are just starting with PyTest, so it's from the very beginning, but we're going to cover some testing principles as well. There's some example code for you to follow along with, including a web app that's written with Connexion 3 and Flask 3 that we'll be testing. You can download the material there. It'd be good if you can follow along. So let's make a start. So I've got quite a history with testing. My first job with Python as a developer was in London working for a fintech startup. And we did full test-driven development there, and I worked there for 4 years. We did full extreme programming, so all pair programming, etc. And I learned an awful lot about testing, and I became passionate about testing as a way of ensuring a minimum level of quality, a minimum level of confidence in your code. And I learned an awful lot about stuff, including over-testing, particularly when your tests are very tied to your implementation. So then as soon as you want to refactor and change things, your tests become an impediment rather than an advantage. And we found at that time that the end-to-end tests that we wrote, the functional tests, which are the sort of tests that QA folk tend to write, interacting with the application from the point of view of the user, that those were the most valuable tests because they gave us the confidence that actually the product worked. I became a Python core developer, went on to work on unit test, which is the Python standard library testing tool, and wrote unit test.mock. So this talk is about PyTest. And if we start at the bottom of the slide, the purpose of testing is to verify behavior. So it's not to verify implementation details. It's not to verify we're using the state machine pattern. What we're interested in is the behavior of our code. And we'll talk a little bit later on. I'll talk a little bit about the different types of tests. So PyTest is the de facto standard now. It's very widely used. It's extendable by plugins. PyTest async.io if you're doing async testing. But what is PyTest? Well, PyTest is a command line tool that we're going to use for running tests. And it's also a framework for writing tests. And we're going to use it in both ways. So before we work with PyTest, we need to have access to PyTest to be able to use it. So this is the layout of the code, the example code. Here's the app we'll be testing, and there's a bunch of files in this directory. Pipfile is how we specify the dependencies. Those are things that we're using, and here we're using Connexion and Flask and UV loop, but we're also using PyTest. So if you do pipenv install, here's one I prepared earlier. Or I can just do pipenv shell to activate the shell where all of those tools are already installed. So if I do which PyTest, this is my virtual environment. It's a local Python install, so I can add whatever I want to it and blow it away. And PyTest is in there. So if we go back to this slide, this shows creating the output of running pipenv install. It creates the virtual environment. Then we go do pipenv shell, which activates the virtual environment. It will also, if we've got a .env file, set the environment variables, which can be really useful. And once the virtual environment is active, you can see if I do which Python, I've now got my local version of Python instead of the system one. If I do which pip, I've got the local pip. So I've got my virtual environment, I've got all the dependencies installed. So I can now run PyTest. And it works. So when we run PyTest, it finds and runs our tests, most of which will be test functions. And there's a naming convention. PyTest is great about conventions, making everything as lightweight as possible. So it looks for files called test underscore and then something. They may well be kept in a project or package directory called tests. And your tests, when you collected all the tests for a project, that's a test suite. Bit of terminology. You don't have to use functions for tests. You can write test case classes. which is a useful way of grouping tests sometimes, but generally it's simplest to write functions. Okay. So again, the functions that we write, here's a couple of simple examples. They follow the same naming convention. So test underscore something. This means we can have in our test modules, our test files, we can have a bunch of tests, but we can also have support functions, other functions that aren't actually tests that are going to be used by our tests. So that's the test name. So pytest looks for all of these files. It finds all of the functions in those files. And we use asserts to actually specify things. So the point of a test is to verify behavior. We want to use our code and then check that it did the right thing. And that's what we do with assert. So assert actual value is equal to expected value. That's the assert there. And we put actual and expected because it reads more commonly, more naturally. And if the test fails, we will get a message. So those test first. Here's a couple of .py. Here's a couple of functions. Here we calculate some value, and we assert that the result is as we expect. So when we run this, that should pass. Here again, we do the same thing, but here we've got the wrong answer. Our expected value is wrong. So we're going to see a fail. And I'm going to use a couple of command lines to simplify. So I'm just going to run an individual test. I'll explain the command line options later. So I'm working here. I'm using Visual Studio Code, working at the terminal, which is the way I find the most convenient to work. Okay, pytest.py test function, and let's disable warnings. Some nice quiet output. So test underscore function. I've got a bunch of things called test underscore function. The one in test first ran and passed. Okay, let's do test failing test. Let's see what happens when we've got an assert that fails. We get the failed message, everything is in red, and we get a nice trace back. This is the line that failed, and pytest shows me what the value for a result was there. So the actual result I got was 3. We were expecting 4. So there's something wrong. The test fails, and we get this nice output that shows us. So that is a significant chunk of what you need to write tests in practice. There's an awful lot of detail, though. Typically, you're going to be calling your code in some way. We'll get to that shortly. But certainly, in terms of getting started with writing tests, you need access to pytest. So use pipenv and install pytest. And then you write test files with test functions in them using the assert statements. You can get a long way with not much more knowledge than that. We don't just have to test for equality. We can use any of the comparison operators. Not equals, less than, greater than, less than or equal to, greater than or equal to, and the is and is not operators. And there's some simple examples of that in the rest of that test first file. This is testing, these last two testing for on object identity. We covered object identity in one of the previous sessions on generators, references, and assignment. I think iterators, generators, references, and assignment was the topic. Okay. So let's run this. Let's see what happens. Let's run the whole of the test first file, and which you should find that most of them pass, except for that one failing test. I can run it. If you want to see a bit more information about your test run, you can add the V or the VV for increase the verbosity. And there we can see all the tests that passed and failed. If you do have any questions or anything you want to point out as we go, do please let me know. So there we go. We've written a test file. We've written a couple of test functions. We run the tests with pytest. Pytest is a command line tool. So there are a whole bunch of different types of tests. If you're in QA, what you're probably writing are functional tests, end-to-end tests. And the point is that they verify the behavior from the point of view of the user. That's really useful when refactoring, as I've explained, but it's also really powerful for CI/CD. We can have confidence that the product works as specified, certainly for core functionality, because we've tested it. Once we find bugs and fix them, we can put tests in there to make sure that they don't come back. There's an awful lot of value in these automated end-to-end tests. Those, by their nature, require spinning up the whole system, and some systems can be complex and use many other services. You may still have to do some mocking in order to mock out the behavior of some services that you can't use in your tests. As devs, we more commonly try to write unit tests. Those are to verify the behavior of your individual components, and often those tests specify the behavior as well. Not every component will have documentation, but if you look at the tests, you can see how it's used and see how it's behaved. And the point is that we test to the unit of behavior, not to the unit of implementation. If you test your implementation details, you're going to find your tests aren't really telling you very much. And also they're a real pain if anything changes. And the point of unit tests is that you want to be able to have a lot of them. So they should be fast and ideally not touch the network or the database or the file system or anything like that, which means we often use mocking. There's a third kind of test as well, often called integration tests, and those verify that your components work together, wired together. Over-testing is a thing. There's a real balancing act to work out how much testing to do. So if you've got good unit tests and you've got good functional tests, then you're in a very good place and better than most places. I find at Gigaclear, we don't write very many true unit tests. Most of our tests are integration tests and that kind of level. Still useful. Okay, so those are the different kind of tests and the language we use to describe them. Code you're actually testing, we call the system under test. And if you've written your code in a modular, decoupled way with as many pure functions as possible, as little state and side effects. Side effects are like writing files, printing to the screen, things that are harder to test. So if you've written your code in a modular, decoupled way, it's going to be easier to test. Pure functions are easy to test because they have deterministic input. Always gives the same output, something with state, something that stores data, stuff in memory or in data in a database. So stuff changes are harder to test, and you have to put things back the way they were. Okay, so if we're setting up the system under test, we want to test the behavior of our system. We need to run it. We might need to put some test data in place or mock out some external services. So we need to set up the system under test. And we can do that in PyTest using something called fixtures. So to use fixtures, there's a lot of text on the screen. Let's have a quick look at an example. Let's go to test2.py. Second. You use fixtures by declaring them in your test function. So here's a simple function. It tests our web app. It takes the test client as a fixture. It fetches a web page and checks the response. This is the response we ought to get from this app. So this is a good point to take a quick look at the app. This is written with connexion 3 and Flask 3. So you'll see those in the pip files, but there's not a whole lot to the app. There's a bare bones create app function. I've got a simple class that acts as config. There's some very simple values in it. We create a connection Flask app, set the configuration, use some of the connection middleware to do cross-origin request spoofing. Is that what CORS stands for? Some protection. Set up the Swagger UI. It's not really set up in this app, but this is how you do it. And then load the API definition from the spec YAML file. And this spec YAML file defines two endpoints, a health live endpoint, which is hooked up to the app.healthLive function, and a gets data endpoint, which fetches some data from Salesforce, and it takes a key parameter. We can see those in the init.py. This is an async Flask 3 connection 3 app. So this is our async health's live endpoint, just returns some JSON. And this is the get data endpoint. It uses a Salesforce client to fetch and return data from Salesforce, which has a result or an error. And I didn't quite have time to implement the get Salesforce client, but we're going to test and mock that out anyway. So this is the little web app we're testing. As you can see, it really is very bare bones, 50 lines and a few lines of YAML to go with it. But the nice thing when we're working with connection 3, if I use pytest async IO, which you'll see here, we can test with async web apps. Okay, so back to fixtures. We want to, in order to test this app, we need to put it in place and provide our tests with a client that's able to talk to the application. So this is the interesting thing. And this is also a reason why fixtures can be a little bit difficult to work with. We specify the test client by name. I can't do control click or go to definition because it's just a keyword name, but I happen to know where it's implemented. It's implemented in conftest.py, and we mark it as a fixture with this decorator. So tests specify the test fixtures they use as parameters. In order for the fixtures to be available, it just has to be imported somewhere, which is why it's common to put them in conftest.py, because that's one of the places that PyTest always looks for fixtures, is always imported for you. So it's a good place to put other test helpers as well. So when we run the test, PyTest finds the fixture, it calls you, and it passes the result into your test functions. And fixtures can take fixtures, so you can layer them on top of each other, which can, if you take it too far, lead to fixture hell, fixtures that take fixtures that take fixtures that, and you're trying to trace in your code, where does this stuff actually come from? And you're 7 layers deep into fixtures. And yeah, I've been there. Okay, so once we create the app, the connection actually provides a test client for us. So test second. This is a test function that declares that it receives the test client fixture. So when we're running that test, before it calls that test function, PyTest is going to call test client. Test client is a fixture that takes the app fixture. The app fixture declared immediately above. This could be one fixture, but I wanted to show you fixture layering. And actually, as soon as you're doing fixture teardown, so this is about setting up resources, but in a little while, we're going to talk about cleaning up resources, the teardown. And if you're doing the teardown, it's easier to do that in fixtures that each do one thing. And that, yeah, we'll talk about that in a minute. So test client is a fixture that takes the app fixture. The app fixture takes the event loop fixture. This is provided by PyTest async IO. When I do a test run, you can see I've got the PyTest async IO plugin enabled. You get that just by installing it. And plugins are pretty easy to write. I wrote one for TestRail when I was working for TestRail. So the event loop fixture is provided by PyTest async IO. That just starts the event loop. We're not actually using the event loop, but we're receiving it here as an argument in order to start the event loop. This allows us to write async tests if we want. However, the connection 3 test client is not an async test client, so there are further hoops to jump through if we want to write async tests. So all of my tests are synchronous, but the app is running async. Okay, so we have an event loop. Let's see what happens when we run this test. Pytest, disable warnings, -k, test _app. It found and ran one test and it passed. So in order to run this function, Python calls the test client fixture, which creates the app and returns the test client to us. With that test client, we are able to fetch JSON, fetch endpoints, and make asserts that the response is what we expect. So that was a really simple test to write, and the only fixture we really needed for it was this create app. This is a convention for creating the app. Okay. These are the fixtures in conftest.py, and this is the actual test. Is everyone happy with that? So what tends to happen over time is every test suite becomes a test framework. When you're testing, you write a domain-specific test framework for the applications and systems that you test. You write a bunch of fixtures and test helpers that become your test framework, all built on top of PyTest. So in property service, UE automation, we have a bunch of fixtures that create the browser that will, using the browser, will log in and so on. And all you need to do, if you want to write a test that starts with the server running and with a logged in user, you just request the login fixture, and it gives you a browser object that you can then use to interact with the object. And this is the machinery on which they run. This is how they work. Okay, so that was fixtures. We're going to look at tear down and cleaning up in a bit shortly. Okay, parameterizing tests. It may well be that you want to test the same code with a bunch of different inputs and expected outputs. In really simple cases, then you may want to test some edge cases. So you can either test in a loop, and the problem with doing that is as soon as one fails, the loop just stops. Ideally, what you would like is for PyTest to run all of your tests and just report the ones that fail. And we can do that using pytest.mark.parameterize and specify sets of data parameters for the test. So here we've got test add. We're going to be testing the add function from the operator module. So we want two parameters, x and y, to add together and a result. And note that we would then add any fixtures after this in the function signature if we wanted to use fixtures as well. So the first argument to pytest.mark.parameterize is a string containing a comma-separated list of the parameters. So x, y, result. It kind of looks a bit weird, and it's kind of duplication. But PyTest needs to know which parameters are you expecting me to fill in and which of them should I look for as fixtures. And then we have sample test cases. Those are usually easy to represent with a list of tuples. So here, x and y, 1 and 2, when we add them, we ought to get 3. X and y, 0. When we add them, the result ought to be 0. Minus 1 and 2, when we add them, the result ought to be 1. And here, PyTest is going to create a test case for each of those 3 different combinations, and you can see here how it reports them. Let's make one of them fail. It's third, isn't it? Test 3. Third. Let's have 12 and 97, and check that we get the answer -6. Let's run with VV on. Let's disable warnings. They're tedious. And let's run just test add. And you can see it ran all 4 test cases, and this is the one that failed. And here it's saying, when I add those together, I get 109, not -6. So it's one way of avoiding code duplication, and it's a nice feature. The eagle-eyed amongst you will have noticed that parameterized, we mark the test using pytest.mark.parameterize, and that's what PyTest uses to create those tests. There are a bunch of other marks that we can use. Sometimes you might find you've got a test which is too flaky, it's failing, it needs to be fixed, but in the meantime, you need to get the pipeline passing. So you can add pytest.mark.skip, and you can specify a reason if you want, but that will skip the test. Perhaps more generally useful is skip if, and that's a capital I, and it shouldn't be. Oh, no, that's not necessarily true. Skip if, skip on a condition. So I think I've got an example of that. Skip if sys.platform is win32. You've got some platform-specific tests. You've got some tests that can only work if you've got a particular dependency installed. You can conditionally skip using pytest.mark.skip if you do, it requires that you provide a reason, something it can report in the test as to why it skips the test.
I've done some examples of that in a library. I think that's when using extras.
Right, yes, yeah, that's exactly the sort of thing. Optional dependencies. So if we've got the optional dependencies, we'll test them. If we haven't, we'll skip them. Yeah. There's a converse situation. Expected fail. Mark a test that is expected to fail. Why would you expect a test to fail? Well, maybe it's something you haven't implemented and you're checking the test in early. It's probably better not to do that. A very good use for expected fail. Let me show you what happens with, well, there's what happens with expected fail. I'll show you the test in a minute. But I've been in situations where we're using a library or a dependency or a tool, and it's got a bug in it, and we have to put a workaround for that bug. What you can do is add a test that fails because of that bug, that exposes the bug, and then as soon as that bug is fixed, you mark it as expected to fail, and as soon as that bug is fixed, you're going to start getting X passes. You're going to start getting unexpected passes in your test result that will tell you, right, that bug is now fixed. We can remove the workaround code and remove the and leave the test in place because it verifies that that bug has gone away. And the other thing you can add are custom marks. A useful one, common ones, smoke test and slow. Custom marks allow you to run groups of tests separately. The trouble is, it's all, when you run just PyTest, it's going to run all of the tests. So we might want a way of disabling the slow tests by default. Okay, so I think this is in test 4. Here's a skip if. So I should see that on this machine. I wrote this on a Linux machine. Here's a smoke test. It's just hitting the health live endpoint and asserting we get 200. If we have core tests of core functionality that run really quickly and don't depend on too much state, they're really useful for verifying deploys. We do a deploy and we can immediately point our smoke tests at it and just check that it's basically healthy. So being able to run a subset of our tests as smoke tests against a fresh deploy can give us more confidence about the deployment. Here's a test that's slow because it sleeps for 10 seconds. And here's a test that we expect to fail. So let's just run those. This is test 4. Test not Windows did not skip. I've obviously got the, oh, it's because I'm on WSL. It's going to say Linux, isn't it? Yeah. You can see this was not skipped because I'm not running it on a Win32 platform. And I got an expected failure. If I change that to pass. I haven't actually seen this skip yet. Let's check it does work. But now we've got an exparsed, and we would want to look into that and check. And the test not Windows was now skipped because we skip it on Linux. Awesome. So we've added these custom marks for smoke tests and slow tests. So let's have a look at the command line arguments PyTest takes. It takes a whole bunch of them. Let's run just our smoke tests. Smoke test. One passed. Just run our slow tests. Oh no, because that doesn't work. Because these slow tests, we don't want to run them every time. So what I did is I added a custom command line argument, run slow. And if you don't pass that in, it disables the slow tests. That's done in conftest.py, and it's done using the pytest naming convention. Magic to switch off slow test by default unless you pass -- run slow. So when Python's importing the conf test, it sees these functions and essentially hooks them. These are essentially event handlers for certain events, and PyTest hooks them up. It's not very hard code to read, but you don't need to understand it. You can copy and paste it and adapt it for anything. So it adds a new command line option, run slow. And if you haven't passed it, it skips the slow tests. So PyTest supports custom command line options. We can use -m to run subsets of tests grouped together using marks, -v and -vv to control verbosity, and -k to run individual test files or test names. And there's a bunch of others for spitting out JUnit XML. If you set max fail equals 1, it will stop as soon as it hits a test failure. --lf only runs the test that failed last time. So it can be useful if you're iterating on a bunch of failing tests. You can keep running it with -lf until it's all the tests are passing. And there's a whole bunch more as well. But these are the ones that I don't use much beyond the ones that you'll see me use here. Okay, something that's important when testing, particularly when unit testing your components, is to test exception handling. Test that things raise the right exceptions at the right time, rather than just dying horribly. That they do the right cleanup if an exception happens. You may want to test the exception message. And this is how we do it with PyTest. There's a pytest.raises exception, context manager. And Python will run all of the code contained inside the with block, the with statement. If that code raises a type error, then that's a pass. If it raises a different exception or raises no exception at all, the test is going to fail. And as xinfo, that gives us access to an exception info object, which we can interrogate afterwards if we want to make any asserts about the actual exception itself.
It's one of the most insidious things with test sheets. If you don't check that the error message is the one you're expecting, people quite often end up with untested code for years because it failed in the place you're not expecting. I've seen a lot of that at Gigaclear and elsewhere.
Yeah, the way that your code raises exceptions or deals with exceptional circumstances is part of the API of the code, and it's important that it be tested.
Try not to raise exceptions. That's my plan.
I think it's the same issue if you're testing for a validation error. So sometimes people stop at, oh, I got a 400, that's good enough, when in fact you should check that the error message that's returned is the one you're expecting.
Yeah. We have a current open ticket from Totsko because when we respond to when we send error messages to them, we're sending an empty body and a status code, and they're trying to parse the empty body as JSON and saying this isn't valid JSON. So we're now going to have to add empty JSON bodies to all of our error messages because of the way error handling is implemented. Okay, so let's just change this. This code, obviously, if you try to add a string and an int, we get a type error. This Python is strongly typed, though not statically typed. Let's see what happens if you can see the test fail if we have a different type. We got a type error. We were expecting a value error, so the test fails. And it's an interesting thing to note about the Python context managers. We use the where you use the with statement, you're using a context managers, and context managers are able to handle exceptional exits. They can have code that handles the exception, and they can either suppress the exception, which is what this exception handler does. If the exception type matches, there's no failure, so execution carries on, or they can let the exception, they can run some code and then let the exception propagate. So context managers are very powerful. If you're looking for some good general testing advice, I recommend this article, which I did write. And I think this first one here, intermittently failing tests erode the value of your test suite. I've seen that a bunch of times where a great deal of effort is put into creating a test suite, and then you run it, and some of the tests are a bit flaky, and over time they get a bit more flaky. People add a lot more tests. And the thing is, if you've got 20 failing tests, each of which only fail one time in 10, and a test that fails one time in 10 might be quite hard to fix. But if you've got 20 of those tests, you've got at least 2 failures every test run. People stop looking at their test run output. They start ignoring failures, and the value of your test suite just erodes. So it's well worth the maintenance. A good test suite is really useful. A bad test suite is worth nothing. So there is a maintenance cost and a maintenance burden, but it's worth paying to keep your test suites useful. Always see your test fail at least once. Put a deliberate bug or error in there. Verify that the test is actually being run. It's really easy to accidentally write tests that don't quite call the code you think it does, or that don't actually test anything. See your tests fail. Okay, so we looked at fixtures a little bit, setting up the system under test. Sometimes your system under test is going to call external services in ways that you don't want to do from your tests. So we can use mock objects and inject them into the system under test using monkey patching. Pytest does have its own, but unit test.mock is better, or you can use the Pytest mock plugin. So when we're testing like this, we use the AAA pattern, arrange, act, assert. This is as opposed to the record and replay pattern, which was dominant in Python testing with mocks until I wrote the mock library, preferring the arrange, act, assert pattern. Technically, it's arrange, act, assert, and then clean up. So arrange, we set up the system under test, which may well just be a component or a few components configured. And that arranging includes putting any mocks in place. Then we act, we call the system under test, which may give us a result or may have side effects, which we can then make asserts about and it's the asserts that actually do the behavior verification. So mock objects are useful because we can configure them. We can set return values, we can set attributes or delete them. We can set side effects, like raising exceptions or returning values from a sequence instead of just a fixed value. And then after they've been used, we can interrogate them to check that they've been used correctly. So here's some example code. It's obviously a very synthetic example, which translates to very badly written code. But we have a function which frobulates, and it takes a frobulator and it calls frobulator.frobulate using some of the frobulator state, the frobulator.data. We want to verify this the behavior of the frobulate function, but we don't want to pass in a real frobulator because frobulating is should be tightly controlled. So we create a mock object, and let's actually do this, which it means I'm going to have to go into a shell because I didn't. Let's have a look. So we're going to use Sentinel and call objects from the unit test.mock library as well. Magic mock is the most powerful mock object, and it is, I consider it my life's work. So I literally added magic to the Python standard library. Okay. We have the frobulate function, which takes a frobulator. With which it frobulates. So we're going to create a mock frobulator to instantiate the magic mock object. And the thing about mock objects is they create attributes on demands, .foo, .bar, .bam, bars. You can call these with arbitrary arguments. You can chain calls to so you can see there, there's a chain, this is some object wildly violating Demeter's law, which essentially says anything more than 2 dots is a travesty. Parents shouldn't know too much about their children, children shouldn't know too much about their parents. And then with the result we call .fish. This mock object, if we look at mock calls, it records everything that's done to it. You see there are 2 calls there. Those have been recorded. Something we can do, bar.bam.baz. Was that called? Yes, it was. Assert. There's assert called and there's assert called once, because it's really common that something should just be called once. That's an assert. Assert. Non-callable mock assert called once. Assert called once with. Assert, yeah. And let's put in the wrong arguments. We assert that it was called 1, 2, 3, 5, but it was actually called with 1, 2, 3, 4. So if you had this assert line in a test, it would fail in the normal way. So we can set up a magic mock. Let's make a mock frobulator. Mock frobulator. Magic mock. It needs some data. So we just need some object. Verify. We can use a Sentinel for that. Sentinel.data will always check. Will always return the same object. Mock frobulator, so useful Sentinel object for tests. So we can assert is Sentinel.data. This will be true. So this assert will pass. So we've set some data on our mock frobulator. And we want to set the return value of the frobulate method. populate dot return value. And we'll just set it to sentinel.results. So now when we call frobulate, passing in our mock frobulator, no real frobulators were harmed in the writing of this test. We get sentinel.results is returned, as we would expect. And we can use this call object to make a representation of the call. So we would expect call.frobulate sentinel.data. That's the call we're expecting. So we can do cert mock frobulator dot mock calls equals expected. And if the mock has been used in any other way, that assert will then fail. So there we're mocking out one of our dependencies that we pass into a function, kind of dependency injection. That's a very quick demo of using magic mock objects. There's all sorts of other stuff we can do. Let's set a side effect of an exception. On object. Now, when I call the mock object, it raises the exception I've specified, useful for testing error handling circumstances. There's also ways of the trouble with mock objects. You can call them absolutely any way you want. You may well, what that means is if you pass a mock object in, and it's called with a certain number of arguments, if the function or the object it's replacing can't be called in that way, your mock might actually mask a bug. We're calling this thing in the wrong way, but because we're passing in a mock object, we don't spot that it's broken. So you can use something called auto-specking, and I don't have, I'll probably do another session on just on mocking and patching because it's a huge topic. But if you use create auto-spec, there's an auto-spec argument. You can to patch it as well. It will create mock objects that only have the API of the object they're replacing and only have the same function signatures for all of the methods on that object. So then if you call your mock object in a way that the original object doesn't support, it will fail in the same way. So auto-specking is worth looking up. It is a useful thing to do in your tests. Okay, so that's mocking. Let's look at patching. We must be running close to time. I can't see because I'm screen sharing. We haven't got a lot of time, probably just enough time for this. So the point of using mock is we want to inject it into the system under test. And the way we do that is with patch. And in Python monkey patching things, injecting stuff into our system under test is easy, but putting things back how they were is hard. So Python, so patch does the work for you from unit test import, from unit test.mock import patch. Patch will automatically create magic mock objects for you. You can tell it to use a different mock type, which you may want if you, for example, want an async mock. But if we have code that calls, say we've got code that calls time.sleep10, we don't want to wait for that in our tests. So with patch time.sleep, and I'm specifying the target of the patch as a string. And this is what causes the confusion. So we've got another slide on that. With patch time.sleep as mock sleep, let's do mock sleep dot return value equals none. Otherwise we get spurious output. Let's call time.sleep for 10 seconds. Execute that code. It doesn't sleep at all. But if I call time.sleep now, I'm outside of the context manager. Functionality has been restored. So I can now do mock sleep dot assert called with 10, and I can verify about how the mock was used. So inside here, inside the with statement, time.sleep is patched out, replaced with a mock object, which I can configure how it behaves. And when we leave the with statement, when we exit the with statement block, the original time.sleep is restored. So how do you specify this target? That is, and that depends on namespaces. If you do import this, you will see some of the great wisdom of Tim Peters, one of the fathers of Python. Namespaces are one honking great idea. Let's do more of those. Okay, so the thing is that you don't patch where the thing is defined. You patch the namespace where the name is looked up. So here, let me show you two different ways of using time.sleep. I can import the time module, and then lookup. That's the dot operator is the attribute lookup operator. That's looking up the name in the time module. I can do from time import sleep, and I'm importing the name sleep as a reference to that function into my namespace. If you look at what namespace are we in, we're in the Dunder main namespace. So this code, that is a lookup of the name sleep in the Dunder main namespace. It's equivalent, that code there, sleep, just the name lookup, it's equivalent in this namespace of globals. Look up the sleep name in this module's globals. Or we can do import sys. You always fetch the current namespace as a module object, like this. Effectively, it's this, the name lookup in a namespace. So the point is, if we want to patch this out, we need to patch it out in the namespace where it's used. So this code doesn't work with patch. But you'd be surprised how often you see the equivalent of this. Patching time.sleep, I'm now calling the sleep function. In fact, let's print time.sleep. Let's verify that the patching is in place. And then let's call sleep. This is wrong. You can see time.sleep has been replaced with a mock object, but it still slept for 3 seconds. This is because the lookup, the name lookup, is happening in the main module, not in the time module. We've patched it in the wrong place. You patch things where they are looked up. We're doing the lookup in the main module. So let's do the patching on the main module. And that worked. So a quick look in our code to see if there's anything. Here we go. From .config, so this is from this module, import the config class. But we're going to import it using the lowercase config. So when the create app code runs, the config object is looked up from the app namespace. It's looked up as app.config. So if I wanted to mock out that namespace, that lookup, if I mocked it out where it's defined in app.config.config, that would mock it out in this namespace. But in this namespace, we've got a different reference to it, and it wouldn't affect this namespace. The right place to knock it out is the namespace where it's looked up, app.config. It's a common cause of confusion when using patch. Okay, so there's a couple of test files. Let's have a look, probably test 6. This code patches out app.getSalesforce client. If you remember, that's an async function defined in the app namespace that happens to not be implemented yet. with with patch app.getSalesforce client, replacing it with an async mock so we can await on it. The get SF Salesforce client function returns a Salesforce client. So if we want to configure the client, we need to get the return value. There, I'm setting the return value of the get data method of our mock client. And now when I use the test client to fetch that endpoint, the response should come from the mock Salesforce client. So -k test get data. Let's do test 6. Two tests, both of which passed. This one is a very similar test, but instead of setting a return value for get data, it sets an exception as a side effect. So on the sets, which corresponds to this code here, we should get an error response instead if the client fails. And both tests pass. The trouble with this is all of our code is indented an extra level. The mocking is a bit verbose, the patching, and it's a little bit, it takes a lot of knowledge to write this. If this was something that we were going to do for every test, we might want to put this in a fixture. And there's a lovely pattern for writing fixtures as generators. So here we do the patching in the same way, but inside the patch, the with statement of the patch, we yield the mock. Pytest notices that we've written our fixture as a generator, so it will iterate over it once. It will pass this. It will pass mock get SF client to the test, and then when the test finishes, we return here. We can put any optional teardown or cleanup here. So if you have fixtures that need cleanup, this is the right way to write them. And then we exit the with statement and the patching is undone and the real get Salesforce client is put back in place. So the tests that use that style, they look like we mock get SF client. They do the same. So the test is substantially the same, but we don't have this extra level of indent, and the patching is done behind the scenes in a fixture for us. So that's a nice style of writing fixtures, the generator style. It allows for optional teardown, and we'll see that those tests run just as cleanly and just as well, and with just as many warnings as the previous tests. We're very near the end. So if you're not writing your fixtures as generators, or there's some reason you want to not do that, and maybe one reason might be if you want in a single request to add several finalizers, several teardown or cleanup steps, you can have your fixture take the request fixture and call the add finalizer on that fixture to add cleanup functions. And the very last thing that I will show you, I think in this, fixture scope. I don't think we've got time to go into fixture scope, but it's worth reading about. If we use -rp, we can see print outputs from passing tests. So normally standard out is captured by pytest. So let's do, is it test 8, I wonder, is it in test 7? It's test 7 setup data. There we go, that's the test I want to run. So this is the setup data fixture, which adds a finalizer, and these just both do prints. So in test 7, what's it called? Test setup data fixture. And we need to -rp. And now I can see the print statements. And you see Python separates out, PyTest separates out for you the setup, test run, teardown phases. There was no output from our actual test. So, and that's the setup. And this is the cleanup from the finalizer that I added in the test, that I added in the fixture. There we go. Request.add finalizer. So that's cleaning up data. It's probably, we're so near the end, it's probably worth adding this. Fixtures really are for setting up the system under test, and you can have quite extensive fixtures if you're testing a big system. I've already warned about fixture health, but you may have some of your fixtures that you want to run just once. For example, creating the database, you want to do at the start of the session. And tearing down the database, you probably only want to do at the end. You may have some test data needed for a group of tests, grouped either in a class or a module. So you only want the fixture to run for the first test in the class, and the teardown to run when all the tests from the class are done. And tests that sort of leak state in the application from one test to another, and you end up depending on that state. So your tests only run so long as test X is always run before text Y, and you end up with a hidden dependency you didn't even know there. That then when something starts failing and working out why becomes a real nightmare. So test isolation. Ideally, tests should leave the system in the same state they found it. However, if we want to control fixture setup and teardown, that's something called scope, and we can group them by function, class, module, package, or session. For the last example file there, test8.py has 2 test classes. Every test takes the class fixture, the module fixture, the session fixture. If I just run the test just in this file, the session scope and the module scope are going to be the same. But we ought to see for the class fixture, for the class scope, we ought to see that called twice, once for this class, and then when all of these tests are run, we ought to see a teardown, and then we ought to see another setup and teardown using these class groupings. Here's a function fixture. That's the default. That should be called every single time. So let's run test 8. I did -v instead of -vv. It's an annoying convention, which is different from all the other conventions. Blame Unix. Oh, we do need to see the prints. RP. Someday my prints will come. Here it is. So this is test class 1, .test1. So this is the first test. So the session fixture is called, the module fixture is called, and the class fixture is called. Then we run test 1. Then test 2 starts. And we don't need it. It's not taking a function fixture. So all of these tests run. When that test is completed, oh, I don't think there is necessarily a teardown. Here we go. And then test 2 starts. So we see the class fixture. But the module and session fixtures aren't called again. But the class fixture is. And these function fixtures are called every single time. So that's fixture scope, where you're creating fixtures for groups of tests grouped by module, which is a file, or by class, grouping tests together. And I think the next of these sessions that I do will be on imports and modules and namespaces. And we will look at all of these things. Okay, unless there are there any other questions? I've come to an end of the stuff I have to share with you. Thank you very much.
Thank you, Michael.
Thank you.
Thanks for
Thank
having me.
you.
Thanks.
Thank you.
Thank you.